We need to get to the bottom of this issue for Marco and his tremendous sense of auxiliary electrode compassion.
So brave. He's an electrochemistry hero. I don't care if he identifies as a synthetic chemist. He's a hero to all electrochemists and graphite rods everywhere. Welcome to the Electrochemistry Podcast, where we discuss all things electrochemistry. I'm your host, Dr. Alex Peroff, and with me is my co-host, Dr. Neil Spinner. On today's podcast, we are going to take a look at Marco, who is a graduate student doing some amazing synthesis work developing novel nickel-based heterogeneous catalysts. Marco has spent most of his research career doing synthesis. Whether it was organic synthesis or inorganic synthesis, Marco could be found in the lab running columns or running to the NMR. He could run a mass spec, but when it came to potentiostats, Marco was out of his element. He recently synthesized catalysts that needed to be tested for electrocatalytic activity, and Marco's advisor recommended doing a cyclic voltammetry experiment. Marco was feeling nervous and didn't know where to start or how to begin. Luckily, a previous graduate student in Marco's lab has a lab notebook and had done some electrochemistry experiments, where he kept notes in that lab notebook. Marco dusted off the old lab notebook and started to reproduce the setup. After some scrounging around for pieces and parts, Marco finally put his first electrochemistry experiment together. However, and not surprisingly, testing his new catalyst wasn't working quite as he expected. Marco noticed that the potentiostat wasn't working. He would tell the potentiostat to apply minus 2 volts, but it would only reach minus 1.3 volts. As a newcomer to electrochemistry, Marco was feeling frustrated. Was the potentiostat broken? Why was the applied potential that Marco set not the potential that was being applied? This is Marco's dilemma.
Hey, Alex, do you think that blindly trusting an old lab notebook from like 1943 that was sitting in the corner of Marco's lab a good idea? I mean, this thing is probably more likely to cause a genie to pop out of it when brushing the dust off or like give directions to the fountain of youth than accurate electrochemistry instructions.
You get 3 wishes. Nah, I just need 1. Get out of graduate school.
Yeah, I'm sorry. You weren't specific enough. You fail. You don't get your PhD at all. It was a waste of time.
No. Wait. I get more wishes, right?
Yeah, but you had to waste 2. See, that's how they get you.
The genie pyramid scheme strikes again, this time to claim an unsuspecting graduate student who unfortunately has to do electrochemistry. That's how they get you.
Yeah, well, if I may, I'm going to use our third wish to get some experimental details from the magic lab notebook genie there.
And this genie is using his own lab notebook, so they should know it pretty well. But Marco was doing an aqueous electrochemistry experiment in some potassium chloride electrolyte, about 0.1 molar. He had a graphite rod counter electrode, a 5mm glassy carbon working electrode with his catalyst deposited on it, and a silver chloride reference electrode.
Okay, so right away here, I think I see a problem. So you said Marco tried to apply, down to minus 2 volts?
Correct.
Yeah, so that's going to be a problem. So you see, when you're doing electrochemistry, you need to be aware of constraints with your solvent. So first of all, for example, if you're using water, like in an aqueous system like Marco here, you've got a window of maybe 1 to 2 volts total. It depends on the pH and the reference electrode and things like that, but something like minus 1 to plus 1 volts, something in that area. But so generally speaking, if you're trying to apply minus 2 volts in water, it's probably a bad idea.
Yeah, exactly. You're going to start ripping water apart into hydrogen and oxygen at those potentials. You might read about larger potential windows in other solvents, such as acetonitrile, that can access closer to minus 2 volts. But generally speaking with water, you're stuck to minus 1 to plus 1 volts. Those are just the limits. Just like we've got speeding limits. You can't go too fast. You can't go too slow.
Yeah, exactly. Or like, you got limits on your cell phone data plan, right? If you stream too much like YouTube, and they're going to start, like throttling your data speed.
Wait, doesn't everyone have like an unlimited plan nowadays though?
They do that?
Yeah, I mean, it costs a bit more, but not much compared to unlimited. I mean, it's unlimited.
I'm way too cheap for that. I'll take my data limitations and just like float from Wi-Fi to Wi-Fi my whole life.
the Wi-Fi drifting nomad.
That's right. It's Fast and Furious Wi-Fi drift, starring me.
And while I haven't seen any of the Fast and Furious movies, I can tell you this: it's all about family. family plan, that is.
I've only seen the first one, to be honest, but I mean, I've seen the trailers for the rest. And, from what I've seen, they drove a car out of a helicopter into like the 83rd story of an office building. And then I'm pretty sure, if I recall, The Rock, he like threw the car into outer space, and then he rode like a galactic humpback whale into Jupiter, something like that. All of that happened. But really, the moral of all of those different hijinks, it's like you said, it's all about family.
Speaking of family, Water's family is getting upset when you try to zap it with -2 volts, which is part of Marco's problem. He's applying way too high of a potential to his working electrode in an aqueous system.
Yeah, but didn't the genie tell him to do it?
I feel like if I planted some random notes into any lab notebook, I could get a graduate student to basically do anything.
Exactly. Pour 15 milliliters of Mountain Dew into a small vial. Add sulfuric acid, boil the mixture, and then your nanoparticle synthesis is complete.
But seriously, what was written in that old lab notebook that Marco was reading, I mean, it's somewhat standard to keep a lab notebook, but I'm going to be honest, some of that stuff is probably just straight up wrong. Like, there's no references. The lab notebooks are probably filled with failed experiments, which are useful. I mean, I'm not against failed experiments.
Yeah, I know, but really, like, if only there was some kind of, I don't know, giant, like, corpus of published literature by researchers all around the world, like over, several decades, where they describe tons of different experiments. And, in this bunch of literature, they would give the details of just throwing this out there, of experimental sections, and they could be copied by someone else. But unfortunately, nothing like that exists at all. So Marco was stuck using random parchment from his laboratory.
Oh yeah. Lab notebooks are still notebooks that use, of all things, paper. Like, the lab notebook really hasn't changed since since science was created.
Yeah, there wasn't even electricity when that lab notebook was written, which, come to think of it, kind of calls into the question how in the lab notebook they knew what a potentiostat was.
Yeah, yeah, maybe they had hand-cranked potentiostats that used mechanical energy. Although, no joke, John Albury had graduate students who rode stationary bikes when they were doing a rotating disc electrochemistry experiment. This was back in like the 1960s. I mean, they're pictures. They had real pictures with these bikes in them. This happened.
Yeah, some call that exercise. I call it torture.
I know you like exercise. Don't try to fool me.
Yeah, I like basketball. I don't like bicycles.
Okay. Yes. Yeah. You don't like bikes. I remember. But I do argue that bikes are probably one of the single greatest inventions when it comes to converting human biomechanical motion into pure linear motion.
And when it comes to touring de France.
We're so American and corny.
That's guilty as charged on both accounts.
Okay, so cycling back to Marco.
I see what you did there.
Applying -2 volts to water was definitely not a good idea, but it doesn't explain why a potentiostat failed to get to -2 volts. Like, potentiostats have ranges above -2 or lower than -2 volts when you try to set the voltage.
Yeah, and when you tell a potentiostat to apply a certain potential, like -2 volts or whatever you happen to be doing, and it doesn't get there, like in Marco's case here, I can tell you usually it has something to do with the counter electrode. And I'll also add that this is, well, frankly, it's kind of interesting because we do tend to focus a lot, as electrochemists, on the working electrode, like whatever experiment we're doing, the reaction of interest is on our working electrode, or we focus on the reference electrode because, well, frankly, most of the time the reference electrode is where the problems happen. Yeah. But really, most electrochemistry experiments, we take the counter electrode for granted.
Yeah. The counter electrode has feelings too. It doesn't want to be taken for granted.
Yeah. I'll bring it some flowers the next time I'm in the lab. I mean, I feel bad. I want every counter electrode to know that it's deeply appreciated.
Platinum isn't the only counter electrode. Marco was using graphite. Graphite has feelings too. Graphite is always secondary. Everyone usually picks platinum, but you know what? Not Marco. Marco doesn't take graphite for granted.
Yeah, that's why we need to get to the bottom of this issue for Marco and his tremendous sense of auxiliary electrode compassion.
So brave. He's an electrochemistry hero. I don't care if he identifies as a synthetic chemist. He's a hero to all electrochemists and graphite rods everywhere.
Yeah, so Marco's graphite rod is definitely something we need to look at here. It's probably the key to why the potentiostat's not reaching -2 volts.
So graphite and platinum are typically used as counter electrode materials. Part of the reason is that it's relatively easy to maintain charge balance when you're doing a reduction at your working electrode, which Marco's doing. He's applying -2 volts. there has to be an oxidation reaction of equal charge and hence equal current that has to happen at that counter electrode.
Right. But also remember, in electrochemistry, usually the current scales with the electrode surface area. So, for example, if you're using like a 5 millimeter OD disc electrode, this is like what Marco's using, right, with his like nickel catalyst coated on top of it, you might expect currents, for example, in the like tens to hundreds of microamps, something like that. But let's say you have like some large metal plate, you're doing, I don't know, corrosion coating test, something like that. You might expect to get like milliamps or even amps of current.
Yeah, so you may have heard this like general rule of thumb that the counter electrode area needs to be about 10 times larger than the working electrode area. So no matter how large your working electrode is, the counter electrode should be much larger.
Okay, so then tell me what happens if it isn't much larger.
Well, okay, so honestly, in most cases, it usually doesn't matter very much, so long as the counter electrode is able to produce an equal and opposite amount of current to the working electrode. The area actually isn't super important. So as long as that counter electrode can drive that same amount of current, it's fine. So we usually set the counter electrode area to be larger than the working electrode surface area. And this is just a way to make sure that, like, okay, you're not trying to send a tiny little bit of current through a small counter electrode area if the working electrode's much larger. So this makes sure that the working electrode current is not limited by the counter electrode current.
Okay, right. But so then there's going to be a risk if the counter electrode surface area is not what you said, like it isn't bigger than the working electrode surface area.
Yes, yeah, exactly. Because in that case, if the counter electrode is unable to generate sufficient current, it will lead to a compliance voltage issue. And compliance voltage issues are a bit harder to find. It's not like you get some kind of warning from, like ED209 from RoboCop saying like a counter electrode issue. You have 20 seconds to comply. And you get this like warning that you need to fix the counter electrode area to prevent the compliance voltage issue.
Wait a second. Did you just reference 1987 American science fiction action film RoboCop, directed by Paul Verhoeven, starring Peter Weller and Nancy Allen?
I did. Yes, I did. And unlike the ED209, you will not get shot by a giant robot if you fail to fix your compliance voltage.
You mean that's not a feature of modern electrochemistry company potentiostats? I mean, what are we even doing here?
Oh gosh, that would be a nightmare.
I think it would be a great way to get graduate students to comply with the rules of electrochemistry research very quickly, although it is admittedly a bit harsh.
I mean, I don't know. Have you actually seen the movie?
No, I haven't. I mean, I definitely prefer romantic comedies to movies about fake humanoid robot law enforcement creatures rampaging around San Francisco. Is it in San Francisco? I assume it's in San Francisco. Every movie is set in San Francisco. And then in those movies, the Golden Gate Bridge gets destroyed. I mean, to be honest, I've actually never been to San Francisco, but if I ever go, I fully expect the Golden Gate Bridge to be in pieces at the bottom of the river from how many movie monsters and like battles have demolished it.
Well, RoboCop took place in Detroit, so most of the places that were destroyed were factories. There were no bridges, but I think the last movie I saw where the Golden Gate Bridge got destroyed was like X-Men: The Last Stand, where Magneto lifts the bridge and moves it to that island.
Okay, so I've actually just looked this up. Ready? Here's a list of movies where they destroyed the Golden Gate Bridge, and I have not seen all of these movies, for the record. The Core, Monsters vs. Aliens, Meteor Storm, Pacific Rim, Godzilla, San Andreas, Terminator Genesis, and then two of just the most cinematic classics you've ever heard of. Sharknado 5 Global Swarming and Mega Shark versus Giant Octopus. Just incredible movies. But that poor bridge, honestly, monsters and space debris see it. They see red. They can't help themselves.
It also gets destroyed by random natural disasters. So sad.
Yeah, I think here Marco, he's going to have to extend his compassion beyond just graphite rod counter electrodes and start a GoFundMe for the Golden Gate Bridge. I think we need to save it the next time there's some gigantic monster invading San Francisco.
Well, if the compliance voltage doesn't get fixed, you'll never have a Golden Gate Bridge problem. I don't care how many monsters or natural disasters occur, because a compliance voltage problem usually means you're unable to do the electrochemistry experiment in the first place.
Well, that's maybe good news for the Golden Gate Bridge, but please elaborate.
So compliance voltage, by definition, is the maximum voltage that a potentiostat can apply to the electrochemical system. Now, you might think like, wait a minute, I know my potentiostat can apply more than -2 volts. But the compliance voltage isn't what the working electrode can apply. It's what the counter electrode can apply.
Yeah, this is a great point. So if you remember earlier, we were talking about the counter electrode and like the equal and opposite stuff. So basically the point that I think Alex made earlier was that the counter electrode has the equal and opposite current of the working electrode. That does not necessarily mean that the counter electrode has the equal and opposite potential of the working electrode.
That's correct. And this is an interesting result of having a 3-electrode system. Basically, the potentiostat controls the potential of the working electrode with respect to the reference electrode. Now, from your perspective, this is what you want. You want -2 volts versus silver chloride, the reference electrode. Great. But from the potentiostat's perspective, it can only control the output voltage of the counter electrode. And by changing the output voltage of the counter electrode and driving current between the counter and working electrode, it allows the user to set the potential between the working and reference electrode. But physically, the compliance voltage is that limit of how much potential the counter electrode can output.
Yeah, exactly. And I know Alex has made this analogy before with respect to a potentiostat circuit. I think we got a video on our YouTube channel about this, but it's a great one. So I'm just going to steal it and repeat it here. But you can think of this kind of thing with compliance voltage like driving a car. Okay, so in this case, let's say I'm driving a complete piece of garbage with 2 cylinders and half a busted engine, right? So I desperately want to go 60 miles per hour. So I floor the accelerator, but no matter how hard I press it, my awful car, it only hits 45 miles an hour. Now, if I were a physicist, I would model my car as a perfect sphere moving on a frictionless surface, and the accelerator would, in theory, speed my car up to like infinity, right? Forever, it would forever speed up, no friction, whatever. But this is the real world, right? There's friction, there's drag, and there's other forces on the car, like the worst engine in history. So no matter how much I try, I can't reach my desired speed. So this is like compliance voltage. It's no matter how badly I want my instrument to apply 1,000,000 volts or -2 volts, whatever, it's slamming against the physical limitations of the circuitry in the way that Alex just talked about. And so really it can't get there. And so really that's probably why Marco was seeing the instrument get stuck at -1.3 volts.
I remember this scene from the Fast and the Furious. Compliance voltage. It's all about family.
It all comes back to family. And The Rock driving cars into buildings. But you know what? I bet the Rock's car didn't have compliance voltage issue. It didn't have any trouble reaching 60 miles an hour.
Because his potentiostat has a high compliance voltage, or it wasn't driving through a highly resistive solvent. Well, knowing The Rock in the Fast and Furious movies, which I, again, haven't seen, I'm going to say they were driving through very resistive solvents.
That's incorrect. The Rock is entirely frictionless, colorless, and odorless. Look it up.
I bet The Rock's potentiostat also has like bright blue, like spinning rims and like a killer racing stripe with a lightning bolt.
Yeah, that's a great idea for our next potentiostat, actually. What about a cell cable with like neon green racing stripe? You get the fastest CVs ever.
Wait, why would the cell cable be neon green? Shouldn't it be like red? Wait, like what color is the cell cable?
Well, our company working electrode lines for our company's potentiostat, they're red and orange. But hang on a second. Wait, thinking about Marco here, what color cell cable leads did he use for each electrode?
Oh, you know what? I bet Marco's Genie Lab notebook referenced different colored cell cables to some potentiostat, but the potentiostat Marco used might have come from a different company altogether.
Oh man, I bet that explains what happened. Every electrochemistry company seems to use a different color convention for their cell cables. So like what one company uses for the working, another one uses for the counter, and then what one uses for reference is another company's ground.
Oh snap. So I think Marco might have switched the cell cable leads between the working and counter electrodes. I mean, that's like trying to push a lot of current through this like small little glassy carbon disc to generate current at this large graphite rod.
It all comes back to the graphite rod, doesn't it?
The electrochemistry hero that we need, but not the one that we deserve.
Wait, now you're quoting Batman? Isn't it like the hero we deserve, but not the one we need right now? I think we're getting our Batman graphite quotes mixed up here.
Throw a cape on graphite so it starts fighting crime. Electrochemical crimes. like compliance voltage.
Well, the only crime I see from this story is a mystical lab notebook from 40 billion years ago that gave our friend Marco here some trouble and terrible experiment advice. Next time, I suggest reading the electrochemistry literature.
Or listening to this podcast, because this kind of stuff is rarely taught in electrochemistry classes or any like hands-on electrochemistry labs. Well, folks, I'm glad we were able to figure out that Marco probably just switched the working and counter electrode leads, which led to the compliance voltage issue. So remember, folks, double check your electrode leads and make sure you have the correct lead to the right electrode. And now, a word from our sponsor.
Here at Pine Research's world headquarters, investigation has been proceeding to develop a line of potentiostat products that establishes the highest levels of customer intelligence, research fabrication, and sustainable machinery in the electrochemistry industry. By placing user satisfaction and revolutionary ideas as the cornerstones of our company focus, Pine Research has positioned itself as the world-leading authority in emerging workstation solutions for laboratory function. Comprised of Wetland mechanical bolts, Spurgis automotive amplifiers and routers, Umstead digital switches, and all monitored by Pine Research software is Pine Research's Wave-Lomatic Electrovoltascape 500. Now, the basic principal improvement is that instead of electrotransmittance being propagated through the neurofiber, it is regulated through oscillatory Weber flux density and bilateral ambidextrous voltammetry. The chassis is constructed from a tremulated alloy of ferrobacaconite that is exponentially wrapped around the electronics in such a way that the anapto chiller sits perpendicularly with respect to the power supply. Additionally, a defect in earlier models that regurgitated axial inductance has been rectified by stamping every third ionic nucleopolar deltroid with a shifting mesodose so as to prevent frontal garbling. Output signals from traditional carriage deplankifiers are often mischaracterized by their entropic homoradiopathy, which is why the mirror stage in our device operates with a positractive jumbo fan to disperse the buildup of charged quantum sieves in motor phasers. Moreover, whenever galvanorelaxive radiance is required, the femtobar can be aligned to 45 degrees so that thermal loitering is amplified, and the angular viscodensity of the sample. The Wave-Lomatic Electrovoltascape 500 research and development has reached innovative maturity and can be purchased wherever Pine Research products are sold.
Advertisement is a joke for comedy purposes and is not real, nor does it constitute an offer of any kind from Pine Research. Restrictions apply. See terms and conditions for details. Not valid in Alaska, Hawaii, any of the contiguous 48 states, or any country on any of the 7 earthly continents, except Antarctica. Contact Pine Research for details, real offers, life advice, or product quotes.
Hello, everyone. Today we are going to play a game of 2 truths and a lie, electrochemistry trivia. So for those of you who are unfamiliar with the game, I'm going to say 3 sentences or statements. 2 of them will be true, and 1 of them will be made up. The goal is that my colleague is going to spot the incorrect statement. That's what he needs to do. Now, the context of these statements is going to be within the realm of electrochemistry history. And I'll tell you, there is some absolutely fascinating electrochemistry history out there. I've prepared 3 statements. 2 are true, and 1 is false. And we will be asking my esteemed colleague, Dr. Neil Spinner here, if he can spot the lie. Neil, are you ready?
As ready as I'm ever going to be.
All right, that's right, because electrochemistry history, quite frankly, is kind of crazy, just like regular history. All right, so let's begin. But first, a quick introduction. In the early days of electrochemistry, around the late 1700s and early 1800s, scientists were starting to play around with electricity by rubbing or just putting dissimilar metals together and creating some static shocks, or at least what we would describe today as static shocks or shocks from like putting 2 ends of a battery together. The effects of these shocks were tested on many different objects and subjects. 3 of the following tests were performed, and as the game implies, one of these statements is a lie. Number 1. Luigi Galvani performed shock tests on frogs. 2. Benjamin Franklin performed shock tests on mice. And 3. Johann Wilhelm Ritter performed shock tests on himself.
And then number 4 can be that I licked a 9-volt battery and also shocked myself. Except that one isn't a lie. I'm still like kind of twitching over here.
Well, if you transferred yourself to 1800, that statement could be there. But honestly, it's not so much when, but where. All these people are from different countries.
Well, I'm happy to lick a battery in any country, any time period or any century, just for the record.
Battery licking that transcends time and space. That's a new field of electrochemistry.
Yeah, that'll be my second PhD topic. Thanks. That's a brilliant idea. Okay. All right. So we've got the frogs, we've got the mice, and we've got dude shocking himself. Okay. Can you give me more details about the first one, Luigi Galvani and frogs?
Yes. Yeah. So if you're unfamiliar, Luigi Galvani, who's named is associated with galvanism and the flow of current. This guy was a physician. So, your doctor, the person who puts a stethoscope on your chest and asks you to breathe heavily. That's the person also that electricity is named after. So I don't know what kind of doctor he was. Maybe he wasn't a good one. So I'm really glad the whole electrochemistry thing worked out for him. But actually, he thought that muscle twitches from electricity were a kind of animal electricity when he was doing these shock tests on frogs. So Galvani and Volta respectfully disagreed with each other about this animal electricity, but I think it would be super cool if animal electricity was actually a separate thing from normal electricity as we know today.
Yeah, that gives new meaning to the unit horsepower.
Tish.
Yeah, wait. Okay, so you're telling me this guy Galvani, he was just like chilling out one day, hanging out, by his local town swamp, and he just had this brilliant idea pop into his head. Hey, I'm just going to start electrocuting amphibians.
Well, when you put it that way, it sounds kind of crazy, but we've heard crazier stories, right? I mean, maybe his career as a doctor wasn't working out well, so he was worried about getting hit with some malpractice lawsuits.
Or maybe he was such a bad doctor he couldn't get enough patients to pay the electricity bill, so he tried turning on the lights with frogs or something. Wait a second. Was there even electricity at all when he was doing these experiments? I think I might have just made a really severe anachronism.
When I read about the experiments, I'm thinking, okay, it sounds like this guy was just rubbing two, metal rods together, like he's trying to start a campfire, and then he just goes around like shocking people, or frogs for that matter. I did have a frog problem in my garage at one point, but I never thought to shock them.
Yeah, you could instead give them to your local high school so they could be dissected in biology class. I think this conversation is starting to get really dark.
Yes, yeah, I think, okay, all right, so that's enough information about Luigi Galvani. Let's talk about good old Benjamin Franklin. I think most Americans are familiar with Benjamin Franklin. He played a role in the founding of America, but he was also a brilliant scientist who was made famous by having an apple fall on his head and tying a key to a kite that got struck by lightning. But Benjamin Franklin also did experiments with electricity and electrochemistry, and he spent some time electrocuting mice to replicate Galvani's experiments. Remember, when Volta came up with the Volta pile, aka the first battery, it was the hottest subject in science. Your nano, your graphene type of stuff, it was the Volta pile. So everybody was trying to build this pile. And yes, it was called the pile. Not a very glamorous name, but these experiments were part of Benjamin Franklin's extensive list of scientific accomplishments.
Why is the theme of this game electrocuting our poor animal friends? I want to play a different game.
Remember, people in the late 1700s were like children looking at ants with a magnifying glass. They were very happy to torture animals for no apparent reason. Although I'm secretly happy about that because we have pesticides, and I really don't like to have insects around my house. So they learned something.
Well, yeah, but I mean, insects aren't animals. I don't want to hear any of you fancy pants biologists, insectologists, bug-loving weirdos about how insects matters, because they don't. But I do have the feels for my poor tortured frog and mouse friends. I don't appreciate the works of Galvani or Franklin at all, if they're even true.
Well, it's not like I'm gonna say we should torture animals, but I mean, we have electricity now, so do the ends justify the means? I mean, we have Netflix now, all because some mice and frogs had to die, which they probably were going to die anyway.
Yeah, when I'm streaming Amazon Prime tonight, I'm going to pour one out for our frog and mouse brethren who, gave their lives so that I can be incredibly lazy.
Wait, that also reminds me. Insectology, that's not a real thing, but entomology is the study of somebody who studies bugs, and etymology is the study of words. I always got those two confused, and I bet if you're listening to this, you're also confused now.
So then, what would you call someone who studies the words that make up bug names?
That would probably be an an entomologist.
Okay, yeah, that's definitely false. Do I win?
Yes, an entomologist is not a real thing. I guess because people who study bugs don't come up with bug names.
Yeah, this is a serious lack of collaboration, and I am appalled.
All right. So let's talk about the last statement, which is about Johann Wilhelm Ritter, which I had not actually heard about or had any idea about him until I needed to make this Echem trivia game.
Or you didn't know anything about him because he's not real at all, and you're making all of this up.
I don't know. Hard to say. But people did some crazy stuff back then. Johann was also studying the pile, because it's the hottest science at the time. And Johann was a apothecary. Apothecary, I can never pronounce that, which is basically a pharmacist. So his regular day job was at CVS, and then he was an electrochemist by night. Also, some other people, Anthony Carlisle. I spelling of some of these names. And William Nicholson were credited with discovering water electrolysis using these early batteries, the pile. But Johann did water electrolysis around the same time, and he actually measured the amount of hydrogen and oxygen gas that was evolved from these experiments. And in addition to his fascination with the voltammepile, he was also interested in light and different wavelengths in light. Now, back in the day, they knew that you could get heat from infrared radiation. So Johann thought, using his brain, hey, maybe if instead of infrared, I went to blue or ultraviolet light, I could create cold. So this justifies the cold gun from Mr. Freeze in Batman and Robin. Of course, we know that ultraviolet light doesn't make things cold, but he did make some contributions to what we now know about the electromagnetic spectrum. But yeah, they say that he would perform these shock experiments, aka electrocute himself using a voltammepile. Some say that he actually died young. He died around when he was 33, was because he electrocuted himself too much. But he also had some bad finances as well that may put some stress. That happens if you're working at CVS.
Wait, before I comment on Johann and his clearly ridiculous life and then try to guess which of these is true, did you just reference 1997 Joel Schumacher directed DC Comics superhero film Batman and Robin featuring George Clooney as Batman and Arnold Schwarzenegger as Mr. Freeze?
Yes, I did. I mean, Mr. Freeze did have a cold gun powered by diamonds, and it was blue. So blue wavelength equals cold in Johann's world.
I bet Joel Schumacher was intimately familiar with Johann's long since debunked theories about blue wavelength light, but decided that it should just be treated instead as scientific fact. Plus, honestly, putting Arnold Schwarzenegger in a silly blue costume and watching him turn everyone into icicles, that was super fun.
Oh man, the one-liners in that movie were crazy bad.
Oh man, they were so good though. Revenge is a dish best served cold. What killed the dinosaurs? The Ice Age. Oh, who can remember? The Iceman cometh. I'm afraid that my condition has left me cold. To your pleas for mercy. And then I think he freezes Robin's diving at him or something. And he freezes him. And of course, gravity doesn't exist. He just stops exactly where he is. And he goes, stay cool, bird boy. Oh, yeah, always winterize your pipes. All right, everyone, chill.
Oh, man. This is ridiculous. Okay, so you've heard the three stories. Do you want to take a guess at which one is the fake story or the fake thing?
Yeah, okay. Well, there were a lot of Johann details and a lot of great Arnold Schwarzenegger quotes. But I'm just going to guess that you didn't make all of those up. So I'm going to guess that one's true. Let's see. I'm just going to hope that at least one of the animal mutilation stories is fake, just for my own peace of mind. So let's see. I'll go with Ben Franklin being fake.
That is correct. Yes. Yeah. So Ben Franklin did not perform shock tests on mice. At least there was no records to my knowledge. I just made that up. Technically, Ben Franklin died 1 year before Luigi Galvani did his animal electricity experiment on frogs. So that was so Luigi Galvani did his first experiments on frogs in 1791, and Ben Franklin died in 1790.
So I guess unless he also invented a time machine, had I known about when these folks lived and died, which I did not. But if I did know that, then that would have been a dead giveaway.
That would be the case. But I do think it's interesting that Luigi Galvani did electrocution experiments on frogs, both living and dead, and that Johann Ritter electrocuted himself. Basically, what you mentioned in the beginning, licking a battery and seeing what happens.
So I think I have two responses for you. First is I'm becoming more and more grateful that like you and I got to go to grad school in the 21st century here and not the 18th century, because I think our degrees in electrochemistry would have been a lot more shocking and painful, if you know what I mean, if we were born 200 years ago. And then the other thing I'd say is, did you just say Galvani shocked dead frogs? Like, that's the most Frankenstein disturbing thing I've ever heard.
So technically, he got frog legs to twitch when he shocked them. So I assume the frogs were dead at that point. So just remember, every time you do a galvanostatic experiment, it's named after the dead frog legs guy.
Okay, well, now I'm equal parts educated and disgusted. I think we probably should wrap this game up.
Yes. And thank you for playing Two Truths and a Lie, Electrochemistry Trivia. And stay tuned for the next episode of the Electrochemistry Podcast.